Am I audible now? Can someone please confirm, or if there is an echo or something?
Clear was clearer.
Okay, so let's start with today's session, deriving ISP or the specific impulse. We'll start with the thrust equation of the rocket, which is thrust equals to m dot exit velocity plus exit area into P minus PA. This was done in last lecture, last to last, and before that. So this part is known as convective thrust, and this part is known as pressure thrust. So when the nozzle is choked, we know the mass flow rate through the nozzle. So we did this in the previous class, knowing the mass flow rate, deriving the mass flow rate equation. So today we'll start with the exhaust velocity. Again, starting with the energy equation, Hc equals to He plus Ve square by 2. So one important thing, last three lectures are very important if you want to cope up in this session, because those the derivations we did in the last class or the methodologies are being used here. So the engine will be looking like this something. This is chamber, this is throat, this is center line, and this is exit. So if you solve this equation, you will get V exit equals to root 2 times Hc minus He. Basically take this He here to multiply, and then take the square root. And as mentioned in the previous class, H can be written as Cp into T, and we told that Cp is constant. That was assumption. Thermodynamic properties are constant. So V exit can be written as under root of 2 Cp into Tc minus Te. You can take the Tc term common, equals to root 2 Cp Tc. Then you get 1 minus Te by Tc. Most of the things are based on previous lecture because the derivation is getting continued. So then T by Tc. Then you remember we took another assumption that the flow is isentropic. So the isentropic relation of T by Tc equals to P by Pc raised to gamma minus 1 by gamma holds. So you can write exit or exhaust velocity as root 2 Cp Tc 1 minus Pe by Pc raised to gamma minus 1 by gamma. We will see why are we doing this. Now, as I mentioned that this rocket equations are all about manipulations. You write Cp Tc as Cp R Tc divided by R. Basically multiply and divide by R. So, and then you write Cp as gamma R upon gamma minus 1. This comes by Mayer's relation. Then you will get this term as CPTC as gamma upon gamma minus 1 into RTC. Just check the derivation what is going on. Then you substitute this thing here. V exit equals to under root of 2 gamma RTC upon gamma minus 1 into 1 minus P by PC is to gamma minus 1 by gamma. Checkpoint. Now, from the previous class, if you remember, we wrote this C star as under root of R Tc upon gamma of gamma, basically a function of gamma. So this under root of RTC, this under root of RTC can be written as C star into gamma of gamma. Now at the end you will get a beautiful equation. So when you observe this equation, when PE equals to PC, V equals to 0, because when P equals to PC, V equals to under root of some term into 1 minus P by PC raised to some function. If this term is, if P exit equals to chamber pressure, basically there is no exhaust velocity, or basically there is no flow. This is just proving this mathematically. And okay, let's derive further. And yeah, another thing is, in the, this is optimal condition, this is called as optimal expansion. Oh sorry, not optimal expansion, sorry. This is no flow, this is no flow condition. Wait, yeah, this is no flow condition. And another thing is, when P equals to 0, that is space vacuum. So when P equals to 0, V can be written as under root of 2 gamma RTC upon gamma minus 1. This Cp equals to gamma R upon gamma minus 1. Then it can be written as V equals to under root of 2 CpTc. This is when P exit equals to 0. Now some points to note here. So note that P exit is not equals to P ambient, not necessarily. So for example, in the space, if in the space, if the ambient, in the outer space or vacuum, when the ambient condition is 0, pressure doesn't necessarily means that the exit will also be 0. So exit can be 0 only when the area ratio is infinity, A by AT equals to infinity. This is the criteria. So basically you can never achieve this. This is called as ideal condition. So just to mention this point. Now let's do more manipulation. So we arrived till this equation over here, but now we need to replace this term. Let's see what we can do. So we have some relations connecting P by PC to A by AT. So basically how much exit pressure you will get when you have a particular area ratio, because you can define one of this. I mean, basically you can, what is in your hand is area ratio. You can give some area ratio in the nozzle, and then you have to prove that what will be the exit pressure. So we will derive that particular equation now. Basically it's required for designing. So again, mass flow rate equals to rho exit, u exit, a exit, and mass flow rate is equals to PCAT by C star. This is proved in previous lecture, uh, session 3. We proved this particular equation in session 3. So you have these two equations. You have AE here, exit area, you have throat area here. Bring this term here and all this term here. You will get AE by AT equals to PC by rho exit, U exit, C star. PC, yes. And then rho exit equals to P exit by R T exit. You can replace this. So your term area ratio AE by AT equals to PC by P into 2TE by C star. Then you replace U exit as from this equation. This equation number 1 I will write. Equation 1. Then you replace this. Let's see what this equation is. Under 2 gamma t c. Okay. So this will be multiplied by C star gamma of gamma. So basically we wrote, right, this root RTC we can write as C star into gamma of gamma from here. Under root of 2 gamma upon gamma minus 1 into 1 minus P by PC raised to gamma minus 1 by gamma. Let's solve it further. Equals to some manipulation again. This can be written as, let's see, PC by PE we will write at one place into, again we can replace the C star of C star and gamma of gamma and another C star. Basically I will write here, replace C star as root RTC, basically a C star square by gamma of gamma. So C star square equals to RTC by gamma of gamma the whole square. Then you have PC by PE into 2TE upon, oh sorry, just a minute. PC by PE, this term we have, then C star square so the mistake that we did was instead of R I wrote 2 over here, because rho E equals to P by RT. So P is here, RT is here. Okay, cool. Now we have corrected our mistake. This is R. Okay, so C star is, and then gamma of gamma the whole square, gamma of gamma, and then this big term 2 gamma upon gamma minus 1, 1 minus P by PC raised to gamma minus 1 by gamma. Nice. R cancel, 1 gamma cancel, equals to PC by PE Te by Tc into 1 by into gamma of gamma upon this big term, 2 gamma upon gamma minus 1 raised to 1 minus p by pc raised to gamma minus 1 by gamma. Okay, this derivation is quite complicated, but yeah. Now again, isentropic relation. Isentropic relation, T by Tc equals to P by Pc raised to gamma minus 1 by gamma. So write this over here, then it will be equals to Pc by P into Pe by Pc raised to gamma minus 1 by gamma, gamma of gamma upon root this particular term. Then after simplifying it further, you get A by At equals to gamma of gamma upon P by Pc raised to 1 by gamma under root of 2 gamma upon gamma minus 1 into 1 minus P by Pc raised to gamma minus 1 by gamma. Okay, this is important. Whenever you have any particular type of gas flow, so you will be knowing the value of gamma, and then you want to, and you know the chamber pressure Pc known. So when you know gamma or the specific heat ratio of the gases, then basically you know the gamma of gamma, which is a function of gamma, and you know the chamber pressure. So basically you have to set a particular area ratio so that you get a particular exit pressure. So we have gas tables for this. You can use gas table or make your own solver. Why I'm teaching this is because when you want to make your own solver, then this is useful basically to design your whole engine in a particular code. So design and there is something called as design and prediction code. So if you want to design your engine using your numerical code, so you can use this equations. Basically I've done all these things in my past. So these equations are very helpful. Basically what NASA CEA does, this is showing you the same thing. I mean, it is doing the same calculations as shown here. So we can use gas tables for this. Now let's go a step further and come back to the topic of getting the ISP, deriving the ISP. So again I will write thrust force equals to m dot u exit plus a exit into p exit minus p ambient. Okay, and we know that a by at a by at is a function of p by pc, pressure ratio. Area ratio is a function of pressure ratio, and ISP we have specific impulse, that is thrust per unit mass flow rate. So ISP can be written as F upon m dot equals to m dot u exit upon m dot plus AE upon m dot PE minus PA. M dot cancel over here. Here m dot I will write as PCAT by C star. So ISP equals to U exit plus A by AT C star. Oh sorry. A by AT into C star by into PE by PC minus PA by PC. I can write this in the simplified form. Now I will write this. I will write as equation 2, and from equation 1 we can write ISP. Equation 1 is basically getting the exit velocity here. This one from equation 1 I can write the whole ISP as C star gamma of gamma under root of 2 gamma upon gamma minus 1 minus P by PC raised to gamma minus 1 by gamma. This term plus A by AT C star P by PC minus PA by PC. And now C star, you can see is common here, equals to C star whole bracket. Now you will see why what is coming at the end. Gamma of gamma under root of 2 gamma upon gamma minus 1 minus P by PC raised to gamma minus 1 by gamma plus A by AT into P by PC minus PA by PC. Now replace A by AT as a function of P by PC. Then you will have ISP equals to C star into big term. And this big term is a function of gamma and P by PC. So for if you define a area ratio, you will know the exit pressure. So you will know P by PC. I'm telling you how to derive ISP for your particular propellant type. So this second big term we call it as CF, that is thrust coefficient. Now if you design a particular propellant type and you know the area ratio, that is A by AT, so because of which you know the, and you know the gamma of your gases, so you know the, I will actually write it down. For your engine, you know gamma A by AT, because of which you know P by PC. And if you know, if you, and basically you know PC because which is set by you, and you know the temperature, chamber temperature, then basically you know C star. So you know both. If you know this, you can calculate your engine's ISP. So I was writing in the previous classes that ISP equals to C star into CF. So C star we derived in the previous class, CF we derived today, which constitutes whole ISP. So this was about the ISP in today's class. Any doubts? Because now we will be shifting to NASA CA of solid rocket propellants. So this today's session was basically to give you a feeling of how ISP is derived mathematically, so that you know how this NASA CA and all this software calculate the ISP. Basically, you can also make your computational model for engine design and prediction if you want. Then these equations will help you. So yeah, I am open to doubts now. Any doubts?